Hey everybody, this is Larry. This is February 27 or 28th, depending on when you're watching this. Here I am trying to do an extra problem. Maybe we'll do something funky for Leap Day. I don't know. Maybe we have to do first. To do a random one, but we'll see. Anyway, today's extra problem from Larry, premium problem from Larry, is 2863, maximum length of semi-decreasing subarrays. A medium problem. You're given an integer array nums, return the length of the longest semi-decreasing subarrays of nums and 0 if there's no such subarray. Okay, a subarray, we know what a subarray is. Maybe. I get that wrong a lot because I don't know, I just kind of read it wrong sometimes. But anyway, a non-empty array is semi-decreasing if the first element is strictly greater than its last element. Okay. And we're trying to find the length, right? So here we look at this one. I guess 7 to 1 is going to be one of these. 6 to 1 is one. 6 to 2, right? 11. Oh, 7 to 6. Wow, I missed this one. All right. But, whew. I mean, I guess it just seems like, find the last number that is greater or sorry smaller than this number, right? So there are two ways to do it, right? You can think about, okay, if this is the first element, where to go for the last element, right? Or you can think, if this is the last element, where to go for the first element. Not quite sure which one is easier yet, but I actually have some idea, maybe. And of course, the first thing to note is that we have to take a look at n. If this is n is equal to 10 to the fifth, which I actually expected, but if it was like 100, obviously we just gotta ignore it. We do it n squared and we go home, right? But so you have to kind of be mindful. And remember that there could be negative numbers, which shouldn't be a big issue, but yeah. Okay. So the way that I would like to think it is, and actually I'm wrong on this actually. I said that if given a 6, I want the first number that's bigger, but that's not true, right? We actually want the first, like, or the farthest number that is bigger, right? So what does that mean? To be honest, initially I thought it was going to be some I thought it was going to be some mono stack type thing, but now that I think about it a little bit more, I'm not so convinced. I think maybe it is a sliding window greedy. Because the reason why you could do that is that you can kind of greedily keep on adding numbers until you see the. Maybe that's an. I don't know. Maybe it could still be monostack now that I think about it. Because I think in terms of, instead of phrasing it as, for example, 7 and trying to find the longest number, you can maybe 7 find the next number that is 7 or greater, right? And that is a monostack problem. And 6, find the next number that's 6 or greater, because then now you just want one index before that. I think that should be fine then, right? Yeah. Yeah, okay. So I think that's basically the idea, is that we want so for each element, we will assume that this is the first element, and we're trying to get the next number but that ends the streak, which is the greater one. Okay, so I mean that seems, I mean I wouldn't say it's straightforward, but it is a problem that I've done a few times, so it should be okay. But I feel like I struggle with this a little bit more than I should, so we'll see. Okay, but first we'll go from left to right to left. Right. So, or maybe I could just do something like for x in nums, right? And maybe we have a stack set up already. And the idea here is that, and maybe we have a sentinel. So a sentinel would be, say, some infinity value, and we have the index n maybe, maybe n, either n or n plus one. I don't have one quite, right? And then now we go, while x is greater than or equal to stack of the top of the stack, the first value. And this is because and I go over this a lot, so I don't know how detailed I want to go over it today. But basically the idea here is that we're trying to say that this number that we have here in the future is not possible for numbers that are smaller than here to be the next big number, right? And here maybe we can I could explain this a little bit better. But I mean, yeah. So like, for example, let's say the next number here is, okay, let's say we kind of compressed everything where 7's bigger than all these numbers anyway. So we have 7, 10, and 11. And let's say we add a random number in the front. Well, if the number in the front is going to be 5, then the next bigger number is going to be 7 anyway, right? If the next number is bigger than that, then it could be other cases. But let's say, okay, the next number is, say, 9, right? Then what happens? Well, that means that this 7 we can remove, because 7 can never be the answer going forward. Because let's say the answer is, say, 5, then the answer is going to be 9, right? Then like we look up 5, the answer to our query is going to be 9. If the answer is, say, 8, the answer is, I guess it's still 9, sorry. But like, let's say the answer is 10, then the next one is actually going to be 10. And as a result, 7 can never be the next answer. And that's basically what this stack does, or this while loop does, is that it has this invariant that x can, or the top of the stack can no longer ever be the answer, right? So here we pop, and then here we append x, and then I guess index actually, but I don't know why I wrote it like this. I mean, I know why I wrote it like this, but it's a little bit awkward. Actually, I'll write it back to the other way. X is equal to nums of index, right? I guess all we had to do is store the index if I really wanted to do it. Okay, fine, that's not really a big deal. But yeah, okay. But then now here, before we append it, then the top of the stack is the next element, or it contains the next element that is, in this case, actually, if it's equal to, actually, we want to end before, so we don't actually pop. But it's a little bit awkward because it does contradict a little bit of what I said earlier, where it can possibly be the answer. Because in theory, it cannot possibly be the answer, but it is the second way. So then here we can do something like best max is equal to, so this is the current is index, and the previous is going to be the top of the stack, the one element, right? Yeah. And here I think this is right because we don't actually count one of the elements. Otherwise, you have to add one, right? We don't count this element because that element doesn't is not on the semi-decreasing subarray. So yeah, all right. I believe this should be good, but I mean, I make a lot of mistakes. So, all right, this is no bueno. So it could also be possible that I miss wrong on this answer, but yeah. Let's see. All right, 63 is 1. I guess that's true. I don't even know if that's true, actually. This should be 0. Maybe I have to handle that a little bit better. But we'll fix that after we kind of debug this. 60 is 1, okay. I mean, technically still no, but okay, fine. 64 is 3. That's actually true. 59 is 1, still no. 63 is 2, that's true. 58 is 1. Oh, did I misunderstand this problem? I did misunderstand this problem. Because it only matters the index C, so it can actually go bigger. I didn't really, I totally I think I got misled here. Okay, so I think I get why this is wrong. The answer is because maybe you have something like I don't know. I can't really find it right now, but even like 60 to 59, this that's 5, right? Even though 61 is greater than 60, but that's fine according to this problem. So okay, so I totally missed. I thought that everything in between has to be lower in some order. It doesn't have, I don't, okay. I mean, I even said that. I thought that the first number has to be the biggest, but now that I kind of look at it, I guess that's not actually true. Okay, so sorry, friends. I wasted a lot of time. Lucky we didn't. I don't know. All right, let's. So one thing I would say, at least for me, and it may not apply to you, the hardest thing I find when I read a problem incorrectly is to reset my mind, reset the problem. Because sometimes I have this thing where, I get stuck on like, oh, I'm thinking about this problem this way, so I have to kind of keep thinking about it the same way or something, right? It's really hard to pivot. So I have to kind of figure out how to reset my mind. Okay, so let's try again. So then now we don't even need to do all these funky things, maybe. It's just that for each number, we're trying to find the rightmost number that is smaller than it. Right? Or for a rightmost number, find a number that's bigger than it. To the left. It's a sliding window then? It's not binary searchable because you can have one that's length like 10, but there's no length 9 semi-decreasing subarray. Alright, so I totally misunderstood this. Whoops. Okay. Okay, so I think the way that I would like to think about it is think about I think it's tricky because we don't want, because I'm trying to think about right now, I'm trying to think about a log n solution, like maybe put everything in a tree or something, right? But I feel like there is still some kind of like monostack E problem, but maybe not quite like the way that I wrote it, because it should be the because for example we have this 11 doesn't do anything, 10 does, we put 11, we put 10, we put 6, and then 1, right? So in that way there is like a binary search thing, right? Because in a greedy kind of way, that's a cute problem actually, right? So it's kind of like the monostack, but not really. Because basically I have something like this, right? So you have like possible answers, and I've written it like this. Is equal to say, I don't know, infinity n again, just as a sentinel value. And then now for index in range of n minus 1, minus 1, minus 1, minus 1, right? Just counting backwards, x is 0 nums of index. And basically this is saying if x is less than possible, the top of the stack, 0. I think this is why, but it's a little bit awkward because now I have to do like a binary search the other way, but maybe that's fine, I don't know. Right, so if this is smaller, then we want to push it on the stack, right? And that's it. Really, you only look at the top, so that now you have a strictly decreasing array of possible small values, and then you just binary search for the answer. And the justification for that is that, and we'll look at this one because I think that's actually a little bit more interesting. The justification for that is kind of similar to what I said earlier with the mono stack, but a little bit different because just the way that thing goes out, right? For example, is it increasing or decreasing? Yeah, for example, like 63 is a possible answer for anything really to the left. And then now you have 60. Well, what happened? Well, 60 is going to be this, right? But let's say you have a number bigger than 64, because the next number is 64. If you have a number bigger than 64, you're going to want to use the 63 anyway, because 63 is better. So you never consider 64 as the answer. So then the next one's 59, and then again 63, but 63 will never be a number that you use. If nothing else, you use 59 or 60 or 63, right? So in this way, you kind of build a decreasing sequence of the thing, and then here, so there are two parts, right? One is kind of just updating for future use, which is what I'm doing here. But then the other part is just binary search. This is a little bit awkward, so I'm going to just flip it. Can you? Binary search is so weird. I think this is a daily problem, so I'll try to see, like binary search reverse. Because I think that's what I want to learn to do better, is binary search. I want to do binary search where like it goes backwards, but it seems like there isn't a library function for it, because I want to write like, you know, just using bisect left, but but you know, now it's decreasing and you have to do binary search on the decreasing sequence, which is not quite the same. Can I reverse this? Because you cannot do binary search on a deck, right? What is the clean way to allow us to insert stuff in the front and do binary search library? Maybe not easily then, but maybe we could also write our own binary search. But I guess the way to do it is just set everything as negative, and then now it's increasing. I hate this solution, but it is what it is. But yeah, so then now we want the next number that's this number or bigger to stop. Oh no, wait, what? No, wait, okay. What number do we want? We want the number that is. So okay, so now now let's say it is in it's in decreasing order. We want, well, we want the last element that this number is bigger than. So we want, and I've handled the negatives in my head, which is kind of, I don't know. Look, I'm not smart. So if it is the same, it's not right. We want the next number, which is the smaller number. So okay, yeah, fine. And then like, I guess if it is the same, oh, negative x, not negative 1. It should be infinity or negative infinity on an index, because if it's the same, I mean, it wouldn't be the same anyway because of this second thing. So then I guess we can use left. And then this is the index. It doesn't matter. I guess in this case, it doesn't matter if it's left or right, because this is an impossible value. But yeah, if this number is inside this thing, then we consider it a possible thing by looking at the, oops. Oh man, we used index. So a search index maybe. And then 1. So that's the last index, and then the current index is this. So okay, something like that. Oh, did I forget to put in the array? This array. Well, returning 0 for everything is, well, actually got something right, but probably not great. Oh, I have to change this because of the negative thing. So yeah, now it's, yeah, okay. Oops. That's why I don't like this negative thing. But I mean, we look okay. But let's take a look to see where we messed up. Right, let's just take a look at this. Right. So we want to search for okay, so it thinks 7 is the thing, and where is the S index? Okay, so it thinks -6 and 7, which is 0, 1, 2, 3, 4, 5, 6. So that's right. Oh, in this case now it includes both. So then here we do to add 1 because the way that I did it the other time was a little bit off as a result. Okay, this is off though still. So let's take a look at this one. Where's the 5? 0, 9. Oh no, that's the search index. So 57 go to 2. Is that right? I guess so, actually. All right. 55 goes to 50. All right. Why didn't I just put best here? Maybe I have something weird. That's why I didn't like doing this binary search like this, because it's just so easy to make mistakes. But we'll fix it. We just need to be careful. 6. So 61. 1, 2, 3, 4, 5, 6. Okay. So 61 goes to 58. That's not right. Oh, I added this somehow. Well, possible thing is wrong. The top of the stack. Is that not right? -6. This should not be like this. That's why this is so funky. Because it should be decreasing, right? Which is why this binary search isn't working. But, huh. Oh, this is funky. I needed to do something like that. I knew that I was like, when I kind of changed it, I was like, something feels like I'm missing something. But this is just like a mess. That's why I don't like to do binary search on a reversed thing. It's just, I don't know. Maybe I need to write something so that I don't need to kind of handle this in the future. Maybe I was silly off by 1. But yeah, I mean, most of the problem is just like we're trying to do a binary search on a decreasing sequence, and I'm trying to hack around it. But that said, other than the fact that we misread when Larry misread it the first time. But I think this is a pretty cool problem, because I think you do get this idea of like, I think the idea is actually very similar. And I think I see a lot of people like trying to memorize monostack stuff by monostack and all these patterns. But I generally actually mostly avoid it. Though, I mean, I don't know. I mean, the thing with speed on some of these contests is that, like, for me, I'd rather focus on my problem solving abilities and not my memorization abilities. So, like, yeah, maybe I am slower than some people who memorize monostack problems, but for stuff like this, assuming that I maybe read it correctly the first time, you still get this idea, right? The idea of this invariant and having impossible answers and how to kind of go around it, and kind of, and this, the way that I wrote it here is pretty much how I think about it, which is that we just have a list of possible answers, and that possible answer is like this gradient because anything else cannot be a possible answer. So very similar to what we would have had on a monostack. So I don't know. Hopefully that's illustrative. We kind of went over 2 problems if you want to think of it that way. But yeah, that's all I have for today. Let me know what you think. Oh, just to kind of go over it really quickly about the complexity. This is linear iteration. So, and this is log n. So this is going to be n log n time. And of course, all of n space because we could put n things in possible. So yeah, that's all I have for this one. Let me know what you think. Thanks for watching. Stay good, stay healthy, do good mental health. I'll see y'all later. Take care. Bye-bye.